All right, thank you, thank you, thank you. Now, why am I approaching from the back of the room, right? Well, because there is no difference between the back and the front, right? So nonlinear solving is implicit. It's where everything comes together, and it's finding where does everything equal, right? So, you need a grand entrance for that kind of a topic, right? So what I'm going to talk about today then is nonlinear solving. How do you find when everything is equal? It's also known as root finding, right? What kind of roots are we talking about? Not those. You do need to have those roots, right? So not those roots. So when I'm talking about root finding and nonlinear solving, what am I actually talking about? Well, let's go back to your, third grade algebra, or, well, I don't know how you guys were in third grade, but some third graders maybe were working on problems like this, right? So you have a problem where you say, okay, 2 minus y equals 3x, x squared plus y squared equals 16, right? So what does the package nonlinear solve do? That's what it does. You write down the equations, right? X, y is you have it in a vector. You say, hey, I want this to be equal to 0, and I want this to be equal to 0, and it tells you when x is equal to this and when y is equal to this, then it's equal to 0. Boom. That's all you needed to know. That's nonlinear solve, right? But yeah, okay. What else can you do with it? Well, okay. So there are a lot of other problems where you need to find roots. So here, for example, if you're thinking about, oh, I have a physical model, a ball is falling down, and at some time point, the ball is going to hit the ground, right? If you're doing your simulation, you want to know when exactly did the ball hit the ground, right? Because you need to stop your simulation and change the velocity of the ball, right? That position where the ball hits the ground, where does it bounce? That is an equation that is, position of t equals 0. Find t such that it's 0. Right? So this is a root finding problem. What's another root finding problem? Well, it's chemical equilibria, right? So as I came from the back there, when does the back equal the front, So for example, if you have a forward reaction and a back reaction, you run this sufficiently long, when are the two going to equal each other, right? Finding equilibria, whether it's in chemistry, whether it's in macroeconomics, all of these other disciplines require root finding, right? And so nonlinear solve is a package for doing root finding and solving nonlinear equations. So I want to create a good version of a nonlinear solving package, but what could good look like, right? So I think that when we were coming into this question, we weren't coming out of nowhere, right? We've already developed, say, differential-equations.jl, and so what we wanted to do is take a look at what does differential-equations.jl do, and so therefore, how should nonlinear solve look, so that way anyone who's already using differential-equations.jl will automatically know how to use this package, but then also will have all the same tricks and everything. So to start, let's just talk about the SciML ecosystem, so that way we have a basis of what we want to be able to achieve with nonlinear solve. And so, this is kind of giving you a high-level overview, right? SciML has a whole bunch of different packages, but at its highest level, it's about making solvers all the same. It's making it so that way, if you do mathematical modeling, it doesn't matter what kind of model you're writing down. All of your mathematical models should have the same syntax and optimize in the same way, have the same set of tooling, and have the same options with the same arguments, and also be just as fast, right? And so, all these different tools, solving linear systems, nonlinear systems, differential equations, right? Differential equations is the one that's had a whole lot of Julia-Kahn talks. Linear solve was last year's. Nonlinear solve is this one. You might be able to guess what the future Julia-Kahn talks will be. So SciML is about making it so that way all of this is uniform in the way that we do and act on code, right? And differential equations.jl is not just about an interface. It was one of the key things is that it's able to hit these performance numbers, right? And I guess one of the things that people really kind of come to this a lot for is this, 50 times faster than SciPy, MATLAB, and R on a whole bunch of example problems, which is something where, again, it's not something that only comes from the performance of Julia as a language. Part of this is from the performance of Julia as a language. Another large part of this is actually just differences in algorithms, right? At the last JuliaCon, I gave a talk about why we use things like SIT5 and Vern7 instead of all the other algorithms that are out there. What are the new things in differential equations, the new algorithms, and how is this actually contributing to the performance, right? And it's with these features that we've been able to outperform even, if you look at CVODE and things like that, we're able to outperform a lot of these C and Fortran codes because it's not just a performance difference in terms of writing good, fast code and doing a bunch of numerical tricks, but it's also new algorithms that was part of this, right? And so what we wanted to do with this space of nonlinear nonlinear solving then is similarly find out what are the things that you know from the literature, but haven't actually made it into code yet. And so it's all these things that we were able to handle in the differential equations case. We want to be able to take this same thing and say, okay, stable simulations, automatic parallelism, the ability to do adjoint sensitivities, right? We want to make it so that way any model that you write across the board, not just a differential equation, but also nonlinear solves and optimization, everything should be differentiable, everything should be parallel, everything should be acting the same across the board, right? And not only that, one of the other big pieces that people really like about differential equations.jl is the GPU compatibility, right? So, you can take any of these specialized solvers and you can recompile them to different GPUs, right? So one of the things that's nice about this is that you can compile things as GPU kernels, and so we've actually taken some measurements against directly written CUDA kernels versus the Julia compiled ones, and we're pretty much one-to-one with a hand-optimized kernel, which is about 20 to 100 times faster than Jackson PyTorch, right? And why is that the case? Well, because it's not just using array-based GPU parallelism, it's actually generating optimized GPU kernels to be able to reduce the overhead of the calls, right? Which is something that you don't see from the machine learning libraries. Not only do we hit CUDA kernels, but we also hit CUDA, one API, so Intel GPUs, AMD GPUs, Metal GPUs, and also someone gave a talk, Mose gave a talk at JuliaCon about targeting, IPUs, right? The graph core kind of specialized structures, right? So what we want from anything in SciML, like we want to take this idea and say, okay, we do this with ODE solvers, but now the goal of the SciML organization these days is, can we do this with linear solvers, nonlinear solvers, things for calculating integrals, optimizers, and do all of this as well, Another piece, right? We're doing a lot with static compilation to WebAssembly. So this is a piece where Tim Short has been, should take really all the credit for actually making this work. But there are applications that you can build which are generating the JavaScript from a lot of our tools that have static versions, and you can embed this within JavaScript, and it's live runnable, and it will actually generate the code then that's required to run this within a web environment, right? And so these are things that people are using today with differential equations.jl. We have you can take your ODE solver and do all these things, but you can't really do it beyond differential equations as much, right? Differential equations has all this optimized, but not the rest of Julia solver libraries. Now, one of the other pieces of differential equations that we really wanted to pull over, right, is this whole aspect of scientific machine learning. What is scientific machine learning? Well, it's the idea of being able to build scientific models, right? So for example, you have your whole physical model, and then you want to add machine learning to it. So what do you mean by add machine learning? Well, you want to be able to have neural networks do things like cover equations you did not know how to model, and you want to be able to use that to be able to generate things that will auto-complete your models, build surrogates of your system so that it can run faster, and all of these types of things that, if you haven't seen this whole talk on scientific machine learning, I would say, type in Julia SciML, and there will be many, many videos on YouTube that you can watch, right? So what does this look like in the context of ODEs, right? In the context of ODEs, we say, okay, there is some kind of physical model that you have, right? Some physical model that you have. And then if you actually look at your data, there's something else that your real system is doing. And so your physical model is wrong. When your physics teacher says, hey, we do this derivation, and you have the first order term, and then you say, plus something of dt squared, and you say, dt is small enough, you cancel it out, right? Something about what you just canceled out was actually required to make this realistic, right? And so what we do with this whole SciML organization is we build out these tools so that way you can say, I have this physical model, but I also can add neural networks to it to be able to learn what I maybe did not model before, right? But there's nothing about this, we talk a lot about doing this in ODEs, but there's nothing about this process that is actually just only for ODE modeling, right? If you build your model, say if you're a macroeconomist and you're building models using, a nonlinear solver, and you're saying, I want to find the equilibrium equilibria. Oh, and my model's not giving me the correct equilibria. Well, what about doing a similar process where you're extending it with neural networks and differentiating through it and all this, right? All of these processes are somewhat independent of the type of system that you're solving, right? We focus so much on ODEs so far, but what we need to do is we need to take these ideas and bring them all to these other domains. So if you want to kind of know one of these examples of how this has been used, here's an example that of some researchers that used some of this Julia code, where what they did was they were looking at binary black hole systems. If you didn't know, black holes are rather large, and black holes are in this space where the size of them makes it so that way light does something different, right? And so if you assume Newton's law of gravity, right, which is what's done here, right? So this is Newton's law of gravity written in a rotational frame. If you assume Newton's laws of gravity for a binary black hole system, your equations of motions will be incorrect. So what you're doing here is saying, oh, there's some correction to my equations of motion, which I'm using a neural network, and from just a small amount of data, so this is gravitational wave data from the LIGO experiments, right? From small amounts of data right here, we can learn what is different between Newtonian mechanics and how this black hole actually moves, and then you can extrapolate forward. And what is effectively doing is learning the relativistic corrections to the motion, right? Now, again, there's nothing about this example. I mean, this example is one that I've talked about a lot in the context of ODEs, but there's nothing about this example that is just ODE specific. So the idea behind SciML, right? Why did SciML move from being differential equations.jl to SciML? Well, the reason is because we want to be able to take any way that people can write a scientific model and do all of these types of approaches for every possible type of scientific model, right? And nonlinear solving is one of those. So what we want to do then is we want to bring SciML to Rootfinding, and I can see that there's some nice, definitely the computer that's running this slideshow is different from the one that I built this for. So there's some very nice artifacts here. But the key here though is we want to say, okay, in this stack then is NonlinearSolve.jl. Differential equations.jl was u prime equals f of upt, but now there's another way to write scientific models, f of up equals 0. Can we do to nonlinear systems all the things that we're able to do with differential equations, right? This kind of extra pieces where you'd say, oh, differential equations has this, but SciPy doesn't, MATLAB doesn't. Can we do that to this domain of nonlinear solving? And so the key of NonlinearSolve.jl is it handles all these different forms, right? So for example, there are different forms of root finding problems. So one of these problems is an interval root finding problem, where you say, in this case, I have a problem, so I have f that I want to be equal to 0. Find u such that this equation equals 0. But what I want to do is I want to give it a set of brackets, right? I want to say u can be between 1 or 2. It's a scalar value that's between 1 or 2. Please find the solution here, right? And so this is one type of interval root finding problem, which is an interval root finding problem. There's other root finding problems, which are these systems of equations, where you say, okay, I have a system of equations. I want to find u1 and u2 such that both of these equations are equal to 0, or du1, du2 are simultaneously equal to 0, right? These are different types of nonlinear problems that are covered by this nonlinear solver interface. Are there more that we want to do, though? Well, there's a lot. What we want to do is, we have this whole SciML ecosystem, so we wanted to be able to leverage and interact with it. So for example, let's say you have an ODE system, right? If you have an ODE system, then there's this common question, which is where is the steady state of this ODE system? What is this equilibrium, right? And the equilibrium, well, you can calculate it by finding where all the derivatives are equal to 0. But if you already have an ODE system, say from differential equations.jl, then you can use a one-liner to be able to turn it into a steady state problem, and now it works with the nonlinear solvers, right? And so we want to make sure that we had these interactions. And what about also with the linear solve, right? I had this whole talk about using specialized linear solvers. Well, we want to make it so that when you give your your nonlinear problem, when you choose an algorithm, you can also choose your nonlinear solver. And what nonlinear solvers can you choose, or linear solver can you choose? It's anything from the whole set of the talk of LinearSolve.jl can all be put in here, right? And if you think about it, solving stiff ODEs is actually a process of solving nonlinear systems at every step, which is a process of solving linear systems. So these packages, they're built on top of each other, and they're coupling each other, and they're working together in the way that they're doing everything under the hood. But this is one way to kind of see that, where all these options for different sparse matrix factorizations and everything are all kind of there because every time that we use a linear solver in nonlinear solve, it's using linear solver under the hood. So all these SciML tools are connecting and integrating in very deep ways. Yeah, the way that this computer is rendering the pieces is funny. But yeah, so nonlinear solve, one of the things that we wanted to hit first is that it's fast and robust, right? And this is some of the new benchmarks that are coming off of the SciML benchmarks computer, right? So what we built with the differential equations case is we built out a computer, the SciML benchmarks, that would automatically be able to benchmark all the algorithms every single time that changes are made to it. And what we've done then is we've now extended it to nonlinear solve cases. In fact, there's a test case that we found in the literature of 23 hard problems. They basically say like 23 hard problems in the field of nonlinear solving, right? And so we took those and we created those into benchmark cases. And what we've created now is a lot of these new algorithms, new implementations that we have. They are both the fastest in these benchmarks, but I think that the speed is not even just the thing to mention here. The fact is that this benchmark set was created to try to make solvers fail, right? And what we actually see is that MinPack, so the standard Fortran set of solvers that everyone wraps, say, into SciPy and such, it only passes on 21 out of the 23 problems. We were able to build out 3 or 4 new algorithms, though, that make use of trust region line searches in specific ways that actually are robust to be able to solve all 23 of 23 problems, right? So we're able to, on all these different cases, have some algorithms that are able to be robust enough to be able to solve all these problems without hitting non-convergence constraints, but also being able to have algorithms which are showing up as the fastest in each case. Now, talking about speed, though, I think that a funny case that came up when talking about speed was we were developing this NonlinearSolve.jl, and we actually saw that Mike Croucher, someone from MathWorks, put up a blog post about how there's this, I guess MATLAB had a new version that optimized the Rootfinding package, and it changed it from 5.8 seconds to 1.6 seconds, right? And so we're like, we're building nonlinear solvers at this point. Let's actually see on the same test case, how we're going to do. Mose actually beat me to the punch first, or he responded by showing, that roots.jl gets about 0.46 seconds, right, in comparison to MATLAB's new optimized version, which is 1.6. And what do you think that nonlinear solve gets on this case? We're down to 0.06, right? And then actually my student this morning sent me a message saying, "Oh, can you update the slides? I found a way to optimize this about 5 times more." So it's down, it has another 0 in there as of this morning, but that's on a PR branch, so I guess that's not allowed right now. So, but in a few days it'll get another 0 there. So, but we're basically from the optimized version with MATLAB, where they're proud to put this in a benchmark, is at 1.66 seconds, and we're down to 0.06, divided by 5, right? And so this is like that performance difference. This case was a interval root finding case, but I mean, and this was a case with interval root finding. This is a case with systems of equations. But I think that the key there is really that these algorithms are optimized to be able to take as few steps as possible, and then mix with the different tooling, and then allow for doing things like JIT compiling the function into the solver to really reduce a lot of this overhead, right? Now one of the key things that we were doing with NonlinearSolve.jl is we're putting in compiler smarts as much as possible, right? What do I mean by compiler smarts? Well, we have a lot of tooling these days that allows us to be able to introspect your function. So if you think about it, what is a sparsity pattern, right? So when you're doing Newton's method, you need to take the Jacobian of a function. You need to solve things using someone's Jacobian. But if you knew the sparsity pattern of the Jacobian, you can optimize it, right? And so a lot of people today, if you look at like Python or MATLAB, they say, "Oh, please give me your sparsity pattern," right? But No, we got to do the Julia thing, right? So what's the Julia thing? Well, the Julia thing is, oh, I can bring in symbolic tooling, and if I then use a symbolic tooling on your function, I can automatically discover what your sparsity pattern is, right? And so this can do sparse automatic differentiation using color derivatives and sparse diff tools, and then it will do sparse LU factorizations, and it'll do all this without you telling me what the sparsity pattern is, because we can actually just look at the underlying code. You know, if your code is Julia function, we can have tooling introspect that to find out what is the underlying sparsity pattern of your true function, right? And so we have tooling that is actually optimizing based off of these features and then making use of things like preconditioned Newton-Krylov, and we're boosting this up the stack as much as possible so that way it's just fully automated, right? And so this is, I gave a talk at JuliaCon where I say, you know, I hope that we start to do things that are so good that people accuse us of cheating. This is one of these examples, right? You know, where, you know, you don't give me the sparsity pattern, but we're still going to use your sparsity pattern if your matrix is sparse, because that's the better way to do the numerics. So we're going to do the better numerics unless you explicitly tell us not to, right? You could turn it off if you want, but our defaults are going to do the better thing. And so, you know, what are some other better things, right? So we have tools for automatically simplifying your equations. So here, for example, is a way of writing a nonlinear system using the modeling toolkit version, right? So you can give us code, or you can give us symbolic versions of code, the symbolic version via modeling toolkit. So here's a representation of that, right? So we have u1 minus sine of u5, right? So this is a nonlinear system. And now, you know, okay, this one's easy to look at and say, there's some simplifications you should be doing, right? Now, but can a computer program, if you naively give this to a computer program, right, it's going to do Newton's method. Newton's method takes O of n cubed operations to do the LU factorization. So you actually have a lot more operations just by having the spurious terms in here. So what we have done with this modeling toolkit system then is we make it so that we can define a nonlinear system, and then when you call simplify, it's able to then cut down your system and say, hey, if you solve this, this is all you need to do. All of your other equations can be generated from, you know, if you find u5 by using this, then all of your other values can be automatically generated from that. So therefore, instead of solving for 5 variables, we solve for just 1 variable, and then we give you a way to generate the other ones. And then how does that look? Well, so when you actually take, you know, this is actually runnable code, right? So you take this code, you then say simplify, and then you say, well, my initial value for u5 is going to be here. I solve it, and it gives me one solution, right? And you're like, great. Well, I had 5 equations to start with, and you only gave me 1 solution. Well, the solver itself has a symbolic interface defined on it. So if you ask it, what is U1, it gives you it. You ask it U2, it gives you it, right? It doesn't actually solve for any of these variables. It's learned that the simplest way to solve this is to only solve for U5. Only solve for U5 using this equation and with these ways of writing down U1 and U2, U3, right? At the end of the day, after you substitute, this is only U5 at the end of the day. So it solves one equation, but then it's able to give you all the different solutions. Again, right, you know, this is something that if someone was looking at this as a purely numerical problem, we just cheated. And yes, we did. This is why we're so much faster. Get on my level, you know? So, you know, we want to change the game, right? These are things that we can do with the Julia programming language, so why not make the algorithms just better than just purely numerical, right? And so then the key with nonlinear solve is that, you know, just like what we did with the ODE solver case, you know, it's flexible. You know, I've put in here this is a subset of all the different algorithms. You know, unlike the ODE solver case, we don't have 300 solvers here, but we have, you know, like 40 or something that cover a whole bunch of different cases and a bunch of different ways to be able to change the way that we interact with tolerances, right? So nonlinear solve has something called termination modes, where with the termination modes you can declare, I want to be able to terminate the solver based off of only absolute tolerances or relative tolerances or a mixture, and there's many different ways of defining this termination mode. So it could be kind of, you know, because we found that in different applications, people care about measuring the error in very different ways, and so we made sure that we can handle all these different ways. Now, one of the things that we carried over from the differential equations case is just automated solver detection, right? So here you just say nonlinear problem and then solve problem, and it chooses an algorithm for you because we don't trust you to actually do these things correctly, right? But the key here is that not only does it have automatic solver detection, there's these poly algorithms that we have under the hood that says, don't actually just use Newton, right? There's many different flavors of Newton, right? There's Newton with different trust region methods, there's Newton with different line searches, and so if you really want a robust way to solve things, you can choose this to say robust multi-Newton, which uses a mixture of different tooling and it tries different cases. And basically we could say, if this thing fails, then pretty much all other solvers are going to fail because it's tried a certain combination that we know is robust across the hood. And there's also this fast shortcut nonlinear poly algorithm, right, which is a poly algorithm that says, try an algorithm that's really fast, like Broyden first. If that's not converging on your case, then switch over to a Newton method. Then if you need to switch, choose a line search method, and then choose a line search method that is more robust but a lot slower to calculate with, right? And so it's able to automatically do this kind of switching behavior, so that way you can have this mixture of speed and robustness, but have it be something that you're not actually having to do on your code level. Because when we actually inspect a lot of user code, we see that in some cases they're just like, oh, I really just need this thing to work, so let me just loop through 10 different ways of solving a nonlinear system, different ways of doing Newton's algorithm, just take whatever solution worked out, right? But we've created ways of doing this, which is actually in the library, to be able to make sure that people get good solutions. Now, again, we want to be able to do things with GPU. So there you go. This is what it requires to change a problem to a GPU. You put an array on the GPU. Boom. We're going to have more examples that are about kernel building and all that. But just like the differential equations, it's GPU compatible, and it's able to do things like compute gradients automatically. So if you stick a nonlinear problem in a solve inside of a loss function, you do forward mode automatic differentiation, reverse mode automatic differentiation. I mean, I know that some people here have heard of things like implicit differentiation, right? Well, this does it automatically. So, if you do differentiation of a nonlinear solver, it doesn't matter how many steps you take going forward. You can always go in reverse in one step. And this, the analytical formulas and such for doing that effectively are built into the system and given as part of the chain rules. And so if you just use the automatic differentiation libraries, they have the built-in things to be able to bypass differentiating the solvers and effectively do the better algorithms. This is done automatically, so that way you don't have to really worry about that. So you just stick it in an automatic differentiation loop and it does the thing you'd expect. Next thing is automatic batching. So what is batching? So if you're going to solve the same nonlinear problem with a whole bunch of different parameters, then there's a bunch of ways that you can make use of batch-style U factorizations. So what this shows right here is it says, oh, what if I loop over? I loop over a code, I put different parameters in there, and I solve it, right? This takes 117 milliseconds. But if you use this batched array, so if you use this batch form, the solvers will be able to re-specialize on the way that you're doing the batching and be able to handle the linear solvers in a specific way, such that it ends up being faster than just looping over the problems. So there's specialized tooling then for handling this under the hood. And so together with all of this, and with a crazy way that it's rendered a title, nonlinear solve is effectively what we've done to, what you know and love from differential equations.jl, taking all of that and bringing it over to this domain of just doing nonlinear solvers. As a time constraint, I didn't mention all the different pieces, but again, you have the questions of, can you embed neural networks inside of here? Yeah, you can embed in neural networks, you can train them. And so if you actually look at the library deepequilibriumnetworks.jl, if you know DiffyQ Flux and all the things that we've been doing with neural ODEs, deepequilibriumnetworks.jl is effectively the same thing, but now on nonlinear solves instead of ODEs. So, all of this from SciML carries over, and I hope that you all see the vision of the greater SciML is to do it for every single way of writing down a mathematical model. So, thank you.
Thank you, Chris. It was a very information-dense talk. Very cool. And
I mean, it's sparse if you use the auto-sparse.
You can sparsify it. Yes. Do I have any questions? Okay. Here we have a question.
Hello. So can you comment on benchmarking a root finder versus a minimizer like MinPack?
Yeah. Okay, so yeah, so I guess one thing to kind of mention is that MinPack also does these least square problems as well, right? NonlinearSolve.jl also does least squares problems. We have not benchmarked the least squares problems yet. There is a Levenberg Marquette and stuff inside of there, which I didn't go into the talk, but that piece has not been fully benchmarked yet. We expect the benchmarks will look similar, but watch the SciML benchmarks for them to show up. Yeah, for now, what we've really done is we've just benchmarked a lot of the different Newton's methods and these different ways of doing it. And then the plots all have which things did not fail and then the speed of the things that didn't fail. And so on MinPack, what we see is that actually MinPack fails to solve a lot of the difficult problems, except when you use a Levenberg Marquette, but the Levenberg Marquette is not that efficient. And we could go into different details. The way that we're doing this Levenberg Marquette, we expect it to be a lot more numerically stable because we're using a formulation that is interacting with the nonlinear solvers in a very different way. Nocto and Wright had some things to write about numerical stability. Levenberg Marquette's one of those algorithms where you should never write it down like the textbook says. That's a much longer discussion though. Yeah. But yeah, we'll have more benchmarks come out soon. And of course, we're starting to do a lot of benchmarking again in the optimization space as well. So we'll get a lot more information on MinPack in that area as well. But this is what we have right now.
Thanks.
Do I have more questions?
So how does the batching interact with the poly solvers? Because presumably they can diverge, right? Each solution can diverge in whatever algorithm is optimal or is able to solve the...
Yeah, so the batch arrays right now, so it's going to try to do all the solving. And so one of the principles of SciML across the board is that we don't believe that we should be throwing errors, right? Throwing errors is disruptive. Instead, what you should be doing is you should try to solve the equation as much as possible, and we give you a return code, and in that return code it says converged or not converged with information about what happened with it, right? And so what happens with the batch arrays, they will try to solve it with all the different cases, and you'll get information about convergence from that. It's a difference between, for example, if you take a square root of a negative number, should you throw an error or should you give a nan, right? And we always do the non-disruptive way of doing that. So you'll get return information that will tell you about convergence, but instead of having error throws, because if you do have error throws, batching would give you weird things where if one of them didn't converge, then all of them would error, right? So that's how we handle that case.
And do you lose a lot of the performance benefits if that's the case?
Losing the performance benefit from, what do you mean?
You said batching is a lot faster. Is that still the case when some of them don't converge or?
Oh yeah, I mean it's still going to be the case when some of them don't converge. You'll just get a message that that the entire set has not converged, right? So your return code will give you this information saying that beware of the solution, but it will be this faster thing. Yeah.
We have room for one more question there.
So the last time I checked, ordinary diffie did not use NonlinearSolve.jl, but had its own implementation. Do you plan to eventually support the full NonlinearSolve package, or is this supposed to be so by design?
Yeah. So the nonlinear solvers of ordinary diffie have to do a lot of special things because they're carrying information from one solve to the next. But this is something that is kind of common across PDE solvers and things like that. So the answer to that is nonlinear solve is getting some enhancements to be able to do this kind of caching. There's a reuse PR that's already out there. I was hoping it would actually be done by today, but yeah, Avik Paul, if you're watching this, I told you that someone asked this question, so it should have been done in time, but you're still allowed to graduate. But yeah, I mean, it is something, it's not even eventual. I want it done ASAP. So it will also decrease the maintenance burden, right, to kind of just have it all just be nonlinear solve. I mean, the key though, right, the key difference of ordinary diffie is that a lot of times it'll do one factorization, and then many different Newton solves will reuse that factorization. And the reason reason is because of how that interacts with adaptivity. And so what we're changing in nonlinear solve, so I didn't go into this piece at all, but nonlinear solve has this caching interface where, so all these interfaces that I showed you is, is all, you define a problem, you hit solve, right? If you use the ODE solver before, you'd know that there's also this init and solve bang, you can use it as an iterator. Those iterator pieces exist within nonlinear solve as well. What we need to do to be able to make it effectively do everything that's required for the ODE solvers is we need to make it so that way you can tell the nonlinear solver that, hey, I don't want you to refactorize, and then in the iterator form, have a way to be able to impose that now refactorize, right? And that's the interface that's being changed. Once that's done, then we'll integrate that into the ODE solver, and we should be completely on just one nonlinear solver step. This also means that the ODE solvers will get new line search methods and new trust region methods as well, which is kind of one of the other reasons for doing the project. So, yeah, I was hoping that was done by today, but it's going to be the next few months, hopefully.
Okay, and with all of these cool features like GPU, symbolics, automatic differentiation, I think nonlinear solvers are solved, essentially.
No. There's still a lot more that we want to. I mean, we still have to solve one equation, right? If we could get that down to 0 by, so for example, there are cases where you can know symbolically how to solve nonlinear systems in a way that is, Mathematica has a set of nonlinear ones that it can handle, right? If we can integrate that with our automatic simplification algorithm, we can even simplify out this case, right? So there are more things that we want to do in this. Like I want the compiler to do it all, but it's going to be going on forever.
Very cool. Thanks again, Chris. And